Well, hello, everyone. We're going to get started. Thank you for joining this GNOSIS Connect webinar. People are still joining, but as we only have a short time for these, we won't delay any longer. Just to remind people that we are recording this session, and it would be great if you have the bandwidth to put your camera on so that we know who we're talking to. It's always nice to see actual faces. Please feel free to introduce yourself in the chat, to put questions in the chat, and we will definitely try and make sure that there's plenty of time for our speaker today to take those questions. I would just like, before we kick off, to welcome you all to GNOSIS. As you know, we're a network that now spans across 45 countries, all of people who are have a shared mission to try and tackle the challenges of keeping space safe, secure, and sustainable through forging new collaborative partnerships between researchers and industry and policymakers. And so with that, I also would like to make sure that I don't forget to thank our sponsors, DSTL, CGI, and Astro Agency, who make it possible for us to bring these events together. So without any further ado, I'm going to pass the floor and a very warm welcome to Gaia Roncalli. Gaia is the co-founder and chief operating officer of Ecosmic, which is an Italian-Dutch startup working on driving improvements in collision alert systems and other aspects of space traffic management. And I will let Gaia explain in a lot more detail what it is that Ecosmic are doing and what their current key research interests are. So Gaia, without any further ado, I pass the floor to you.
Thank you. Hi, everybody. Very nice to be here. Thank you, Catherine, for the introduction. So we'll quickly share my screen so that we can start. Okay, so let's see. So can you see my screen properly? Yes, great. So once again, thank you. Thank you for connecting. So today, the topic of this webinar is to understand satellite operators' key requirements for collision alerts. So just to start first, let me explain why I'm here. So again, my name is Gaia. I'm one of the co-founders at Ecosmic. My background is in aerospace engineering. I specialize in astrodynamics and space sustainability at the Technical University of Delft a few years ago. And since then, I have been conducting many interviews, more than 50 interviews with satellite operators from the industry and space agencies, as well as participating into the ESA Zero Debris technical booklet workshops. So let's say that I've been spending most of my time trying to put together inputs from the industry and space agencies to understand what kind of services they want when it comes to the collision avoidance process. So this is my expertise, and this is what I used also to then found Ecosmic with my two co-founders. And Ecosmic provides a software, a service that helps satellite operators manage collision alerts between their assets, so satellites and other objects in space. But today I really wanted to focus this conversation on the point of view of the satellite operator, so the point of view of the end user of these kind of services. And to get started, so first of all, what is the collision avoidance process? So I think we all more or less know why it is important to avoid collisions between satellites and spacecrafts. Of course, we want to avoid destroying satellites, but also creating way more debris in space. And when it comes to creating a service that does the collision avoidance process, there are three phases. So first of all, we need to track the objects in space, so both space debris and satellites and rockets. And those are tracked usually from ground using radars and telescopes, or in more innovative ways lately, there is also lasers, for example, to track space debris. There is then the second phase, which is that with all of this data about the velocity and the positions of the space objects, we want to estimate whether or not there is a risk for a potential collision. And usually there are different metrics that are used for that, from the probability of collision to the missed distance between the objects. And then finally, there is a third phase, the last one, which is basically to say, okay, will my satellite maneuver? Should I maneuver? And if I have to maneuver, when should I do it and how? So these are usually the three phases in the collision avoidance process. And today I'm going to focus mostly on the last two phases because this is what we do in-house inside of Ecosmic. But we also have partners, obviously, that help us track the objects. So we'll briefly talk about that too. Now, if we want to focus though on the end user, so the satellite operator, first I wanted to start with trying to make you become the operator. So let's say that you are a satellite operator now and you are managing some assets for the company you worked for. And you receive in your inbox an email that is a conjunction data message, a CDM. So a CDM is basically a collision alert. That's how they're called. So you receive that in the morning. And what you do with that is that you immediately open it. And inside there's a list of important information with parameters such as the probability of collision and other ones. And the first thing you would do usually is to check the probability of collision and see if it's under a certain threshold or above a certain threshold. And let's say that you receive this alert and you immediately check the probability of collision. And luckily for you, it's under a threshold, the threshold that your company gave you. So you're good. You can disregard this CDM and you just go back to your nominal operations. Then some time passes, let's say a few hours, and then in the afternoon, you receive an update, so a second email on this collision alert, this CDM. And this time, the probability of collision is above the threshold. And it says that the TCA, so the time of closest approach, which is when the conjunction, so the collision is supposed to happen, is in 12 hours. And at that point, let's say that you don't go back to your nominal operations, but instead what you do is you immediately go into the emergency procedures. And emergency procedures really vary depending on the company you work in. So if you work at ESA, if you work in a big company with a constellation of satellites, or if you're part of a startup or scale up. But either ways, what you do is you immediately try to perform analysis with the data that you have on your own satellite and the data on the secondary object that would be involved with the collision that is given to you by a third party. So you perform analysis, you recalculate the probability of collision, the missed distance, and you perform simulations to understand whether or not you are sure that this collision will happen. And in that case, you have to have meetings with your manager. So let's say all of the people in the flight dynamics team, all of the people in the satellite operations team, and you understand basically if you have to perform a maneuver, what kind of maneuver you can do. Now, maneuvers are really disruptive because let's imagine that what you're operating is a satellite that does Earth observation. Usually every day and every week you have a plan that says exactly what you're supposed to do with your satellite every hour. So if it's Earth observation, basically what it says is, okay, we have a customer. Let's say that this customer has ships, and what we need to do is tracking certain ships throughout the Pacific. And of course, your satellite will pass above the Pacific at a certain time, and that's when you should take pictures and then download them to send them to your customer. Now, if this collision should happen exactly while you're above the Pacific, that means that you're gonna have to perform a collision avoidance maneuver in the moment in which you should have taken the pictures for your customer. This is extremely disruptive, obviously, because it's disruptive in the sense that you're not able to provide the service that your customer is paying for. But at the same time, it also means that you have to change the plan, not just for that 1 or 2 hours in which the maneuver will change the orbit of your satellite, but you also have to change the plan for a lot of things because basically this impacts your whole daily or sometimes even weekly plan that you had for your satellite. So you do all of that, you involve all of these people in the meetings to understand what you can do. This basically takes quite a few hours. And let's say that if you're lucky, by 6 or 7 p.m., you receive another update that says that actually the probability of collision is again under the threshold. which means that you don't need to do a collision avoidance maneuver. And basically, all of the hours you spent doing these analysis, simulations, and meetings are actually wasted because there's no need to do anything. Now, this seems quite stressful and also a bit of a waste of time, but this is actually what happens quite a lot when it comes to satellite operators. This is, I would say, a typical day in the life, for example, of a satellite operator that manages a constellation of satellites. Now, why does that happen? First of all, there's one thing to consider, which is that CDM, so conjunction data messages, the collision alerts, are not accurate enough usually. And 99% of collision alerts, actually 99.999%, are false alerts, which means that most of the time, whenever satellite operators perform this kind of analysis to understand whether or not to maneuver, in the end, they will receive an updated collision alert that says that actually the previous one had overestimated the risk. Which means that in the vast majority of cases, this is good because it means that nothing needs to be done and no collision will happen. But of course, it's a strain on the resources in terms of time and money for companies, for private companies that have satellites. Now, why is that? So it seems quite absurd almost to think that satellite operators can receive millions of collision alerts throughout the years and that 99.9% of them are false. And there are multiple factors involved in that. So today I will not delve too deep into them because it goes a bit like technical, but I will try to say what are the most important ones. So first of all, when we go back to the first phase of the collision avoidance process, one thing that we said was important is tracking. So I don't know if you've ever seen an image of a satellite being tracked by a telescope, but this is what it looks like. It's very faint and it's quite hard to see. But basically, I hope you can see that in the image on the right, there is a bit of a streak. And this is the satellite moving. So those are the images that are used then and processed to understand what is the position of the satellite and what is the velocity of the satellite. And those, of course, the more we have them, so the more frequent these observations are, the better it is to estimate the position and the velocity. Now, the issue is that there's a lot of uncertainty involved in the tracking process, which can be both on the side of the hardware that is used, so the telescopes or the radars, that can have up to a certain sensing capacity, but also there are errors that come through the hardware. But there's also errors that actually are there because of, for example, the atmosphere. So the fact that we have the atmosphere means that it makes it harder to see objects. And of course, there are many other issues, such as if the weather, for example, in the case of telescopes, if the weather is bad, and then there are like clouds that block the visual. So there are many things involved in that. But let's say that even just in the first phase of the collision avoidance process, we get images, we get data that already has a big uncertainty. And when I say big, I mean that, for example, for space debris, it is quite common to have an uncertainty of 100, 200, 300, even 500 meters on where it is. So basically it could be here or it could be, like on the other, I don't know, side of London, sometimes even when the uncertainty is really big. Now, this uncertainty, let's say that when then we take it to use it in our algorithms, so including also the ones that we use at Ecosmic to calculate the probability of collision, you can visualize it as basically a bubble around the satellite. So here you see that you have satellite A and satellite B. So in this case, let's say that the potential collision will happen between two active satellites. You have basically these kind of circles that you see around the satellite, and this is basically the space in which we think that the satellite could be. So we don't know exactly where it is. Now, when we get the data from the observations, so from telescopes and radars, the bubble can be, so let's say 500 meters in radius. And this is what we start with. But when we want to calculate the probability of collision in the future, we have to propagate the orbit of the satellite, which means basically propagate both the potential position of the satellite, but also the uncertainty tied to this position, so the bubble. Which means that if you propagate it for example, 1 day or 2 days, what you get is bubbles that are way bigger, so uncertainties that are way bigger. And this means that whenever you try to understand whether a satellite will crash into another satellite, what you're considering is not just the position of the two satellites, but you're considering the bubbles, so the uncertainty of the position. And now what you can see from this image is that even though it seems like satellite B would pass over satellite A, so it doesn't seem like in this case there would be a collision, the two bubbles meet. So you would receive an alert that says, hey, there's a potential collision upcoming. So if you're a satellite operator, you would start doing all of the processes that I showed you before to ensure that you have a way to maneuver away from the other satellite, even though actually, as you can see from this image, there wouldn't be any collision. So the uncertainty that we get at the beginning from phase one, so the tracking process, actually carries on into phase two and becomes even bigger. And this is an even bigger issue when it comes to sending collision alerts, because it means that you keep sending collision alerts that actually are false alerts. Now, this uncertainty is also what we get when satellite operators receive alerts from public SSA, so Space Situational Awareness Services. So when I told you that to imagine that you're a satellite operator and you receive these alerts in your inbox, what you're receiving is actually alerts from usually a public service. And there are multiple public services. The most famous one, which is the one that almost everybody uses, at least from the companies we talk to, which are mostly based in North America or in Europe, is SpaceTrack. And SpaceTrack basically is a service that was part of the Department of Defense of the United States until 2018, and then was transferred to the Department of Commerce. And it's a website that is available to everybody. So you could log in right now, like register and log in. And if you are a satellite operator, you can basically connect this website to the softwares that you use to receive collision alerts automatically. Now, this service, of course, is amazing. It was created to ensure that there could be collision alerts sent to any operator worldwide and not just to American operators, which is obviously the good way to think about it, right? Because we're talking about a problem that is international. So you cannot do things that are only for your own country. And this service has been used for many, many years, for almost 20 years, if I'm not wrong. And is now was now actually like changed since 2018 to be incorporated into the Department of Commerce, and will change name into Trax. So there will be a new website with new capabilities, but the idea is always to send collision alerts to satellite operators worldwide. Now, there's also another service, which is the one from the European Union, which is called EU SST, Space Surveillance and Tracking, which is very similar. And of course, these services, as I said, are amazing. They're free and they're international, so that's great. The issue with these services is that for a very long time, the algorithms used were quite old, which means that they kept overestimating the probability of collision and sending way too many false alerts. This is still happening, even though now both the Department of Commerce in the US and also the European Commission with DG DEFIS increased the funding to make sure that private companies could actually sell their services to the public SSA services. And the idea with that is to increase the accuracy and the performance of these systems. So there will be basically bids, and the best service basically will win a contract. Now, the great thing about that, again, is that we can have better quality and better performance, but still this is basically a process that is ongoing, and we still have basically different public services. Now I'm just saying two, but I'm sure that there are more in other countries that send different collision alerts using different methods and using also different telescopes and radars that are tracking the objects, which means that you get to different results. So for example, if you're a satellite operator and you're subscribed both to SpaceTrack and USST, you're going to get different alerts from both, and sometimes the results will not match. So what do you do in that case? You can see that the situation actually gets even more complicated. And this brings me basically to the last point when it comes to pain points for satellite operators, which is there are no rules of the road. So at the end, the main issue with these services providing different results is that there is no set of international laws that one is supposed to follow when it comes to space traffic management and collision avoidance. So here, one of my co-founders actually last weekend had fun making this map, which is based on data from UNOSA. And you can see here which countries have space debris mitigation requirements that are inserted into national law, which are guidelines, and which countries are maybe still don't have guidelines but are working on them. What's important to note here is that most of these national laws are actually soft law. Up until now, there's only been one case that I know of a company that has been fined for not following these space debris mitigation requirements. This happened a few years ago, or maybe last year, with an American company. But for most countries, and so for most satellite operators, there's only vague guidelines or soft laws that also change from country to country. And the crazy thing here is that, of course, if I am, for example, a Dutch satellite operator and the incoming collision could be with an American satellite operator, what can I do? So how am I supposed to know whether or not to maneuver, and what kind of guidelines am I supposed to abide on if we have different sets of guidelines from our countries? So you can see here the problem. Now, one thing that I wanted to focus on maybe today is to show one way which I believe is great when it comes to putting together these kind of technical challenges, such as in tracking or in the algorithms, together with the guidelines and the more like legal part of collision avoidance. Now, one thing that worked really well and that I participated in were the workshops for the European Space Agency Zero Debris Technical Booklet. So this is a document which is actually now available also online. And it's a document that says what are the enabling technologies that we need and the guidelines that could be used for collision avoidance, and not only, also for other space debris mitigation requirements, which I'm not going to explain today because there are too many, but it's quite thorough. And the reason why I believe that it was great is that they basically put together a lot of companies, from startups to scale-ups to old space, so large system integrators, to also policymakers and space agencies worldwide. And they were all invited to participate into these workshops, where the idea was to come with a draft of this technical booklet and then discuss every single requirement for an entire week. And these happened multiple times. The great thing about that is that you get inputs from the industry and from satellite operators, so the people are actually in the end having to deal with these guidelines, even before writing them. So you just present drafts, we discuss them, then we present a second draft and we discuss it again, etc., etc. And today I wanted to show you a bit of how that worked, because I believe that it was really important to get some more insights on how to draft guidelines and what to improve from a technical point of view for collision avoidance. So one of the questions was, how should we improve collision risk assessment? And basically what we did was that everybody was discussing and then voting what was the impact versus the feasibility of different technologies or different measures that we could take. Here I'm just putting one as an example, where there were basically different things that were listed that could improve the collision avoidance process and collision risk assessment. And here you can see basically what most people voted. And again, here there were people from all industry, all space agencies, but also policymakers. So it was really broad. And here you can see, for example, that one thing that came out was that we need more guidelines and methodologies for collision probability assessment, that we also need open reference and improved space debris population models. So this is also something that usually is provided by, for example, space agencies such as ESA. And you can see that in all of those, both the impact and the feasibility was drafted. And this is important because it also means that ESA can then fund, for example, projects that are considered the most impactful for the industry. Another set here of improvements that was considered, and here you can see that one that stood out, even though it takes a lot of effort, but it's really impactful, is to have better models for atmospheric density and space weather and propagation. So I about propagation a bit when I said that the orbit of satellites is usually propagated for example, 1, 2, or 3 days, and that the uncertainty increases the more you propagate it. But another thing that is considered important is, for example, the atmospheric density, which is really impactful for objects that are in low Earth orbit, or space weather, which also impacts the orbit of objects. So in the end, the uncertainty also on their position. Now, all of this came to actually one important result, which were basically, I summarize it in 3 points. So first of all, we need to share more data. And when I say we, I mean both SSA providers, but also even more so satellite operators. So it's extremely hard, really, really hard to have 2 different satellite operators that could be involved in a collision working on estimating whether or not this collision is going to happen when they have different data to start with, and they don't share the data about their own assets between themselves. Another one was, of course, to have a standardized set of guidelines. Right now, as I said, we have different guidelines and soft law that is different between countries. There are some really nice papers that compare those guidelines, but the issue is that this still does not say which guidelines we should follow. So as a satellite operator, all of this is interesting, but doesn't really solve the issue. And the reality is that we should draft the guidelines all together. And I know that having bilateral meetings is extremely hard, but this is the only way really to get guidelines that are then effectively used by satellite operators. And lastly, better models and methodologies. So I'm gonna just quickly go through the methodologies, just to tell you a bit more about what we did in Ecosmic to improve both the second and the third point. So real quick, in SAFE, so our software, what we did when it comes to the methodology was to improve really how the uncertainty is treated. So here's a case study with a company we've been working with. Here you can see some of the CDMs that I have received, so 18 of them. And you can see basically what our software said that the probability of collision was, what SpaceTrack said, and then we used a benchmark, which is basically the closest to reality, like the probability of collision that is the closest to reality, that is like the white cross. So you can see in a lot of cases, the real probability of collision was 1,000 times lower than the one that was estimated by SpaceTrack, so a public SSA service, which means that, of course, these were really false alerts. And we basically achieve this by using an innovative algorithm. We are going to publish also a paper about this very soon. It's going to be published at the ESA Zero Debris conference in Bonn in 2 months. And another CDM, in this case, you can see instead that the probability of collision was 10 times higher than what SpaceTrack indicated. So again, the idea is that we need better models and better methodologies, so better algorithms to estimate the collision alerts, and there is a lot of improvement that can be made. Still, even though we did make improvements on methodologies, we try to also bring some clarities to satellite operators by saying that if you use our product, you're compliant with most of the space debris mitigation requirements, guidelines, and regulations, just to make sure that satellite operators, if they use our product, they can say, okay, we know that we're compliant. That's it. We don't have to go and check each guideline for each country or each soft law. So here it is. I didn't have much more time, so this is the presentation. Here you can scan the QR code if you're interested in learning more about what we do at Ecosmic, and you have my contact. Now, it would be really great if you have some time to have a discussion, and of course, I'm open to any question about either the technical or the legal part of space debris mitigation. And yeah, thank you for your attention, really.
Thank you. Thanks, Gaia. Much appreciated. I know we try and run these as very quick knowledge sharing sessions, but if people want to hang on and ask a question, please do. There are a couple of questions in the chat, but if anybody wants to put a virtual hand up and ask their question directly, please do that. Now, there are some questions in here that are around actual what you started with,
Yeah.
which is the fidelity and availability of tracking data. But I think people would still be interested in your opinions on that. So, for instance, Stuart Mackerel has asked, is it possible to use GNSS positions to help increase accuracies of the predictions?
Absolutely. Yes, it is possible. And actually, one interesting thing is that when it comes to calculating the probability of collision, usually what happens when you're an SSA service provider is that you have really accurate data on the object of your customer, so that their satellite, which can also be GNSS data. And then you have less accurate, way less accurate data. And when I say way less, I literally mean that sometimes the uncertainty on the position is kilometers. And this is usually the issue, is that you don't have accurate data on the secondary object. Sometimes it is due to the fact that it's a piece of space debris. It is not well tracked, and we cannot do much about it unless we actually ask some of our partners that have telescopes and radars to try to track it for us. But in other cases, it's a second satellite. This is less common in terms of probability. Of course, there are way more space debris than satellites. But when it happens, in that case, it is crucial to have the contact of someone in the other company that owns the other satellite or operates the other satellite, to be able to coordinate. And that's actually when there is this issue of not sharing data. This data about satellites is considered confidential because it is also a security matter in some cases when it comes to sharing the position of a satellite. Which means that in some cases you don't really get an answer. So one thing that I can say, for example, as an example, is the case of a few satellite operators I talked to that were saying we are in the orbits where there are, without giving names, there's a really, really big constellation of satellites in low Earth orbit. And whenever there's a possible collision with them, they don't really reply. So it's kind of hard to communicate. But we know for sure that every time they do maneuver, but they maneuver at the last minute, which is fine for them, for their set of guidelines for operations. But for us, for example, if they work with ESA and they have a more stringent set of guidelines that says that you have to maneuver not just at the last minute, but you have to maneuver, for example, like at least 6 hours ahead or something like that, then we can't really comply with that. But we have no other way. And we know that in the end, this big company is going to maneuver. But for us, it's always kind of a stressful moment, obviously, because we have no certainty and there is no communication. So this is just to give you a bit of an example of how it can go when it comes to collision avoidance.
Thank you.
In America, we call that playing chicken.
Yes.
Blooms first.
I do have a question about the more congested orbits get. This is me just abusing my role as the chair to put my own question. Um, how are the current solutions operating so that, if you decide to act on the collision alert because you think that you have got a good analysis there of the level of probability, how do you know that the maneuver that you're choosing to make is not putting you in the path of another collision?
Yeah. So as an SSA provider, I can say that what we do is that we recalculate the probability of collision with any other object that would be in the orbit that you go into when you maneuver. So whenever you plan a collision avoidance maneuver, one really big important step is to make sure that you don't actually increase the chances of having a collision with a third object, obviously. So this is really important. This is basically, it just means that you rerun analysis on potential collisions with other objects. And this is something actually that in any kind of guidelines or soft law that we have about that, it is specified that you need to do that. On the other hand, though, one thing that you don't need to do necessarily is to immediately communicate the collision avoidance maneuver that you want to do. Which can be an issue in some cases. And even when you communicate it, for example, you don't necessarily get an update on the collision avoidance maneuver that are done through SpaceTrack immediately. So sometimes you get the update a bit late, which means that actually, even though you don't really risk colliding with a third object, maybe other companies will see alerts anyway in their inbox because of your collision avoidance maneuver. In the end, nothing will happen. You know that you conducted your analysis, so you know that you're safe. The issue is that the other companies will not know necessarily like immediately that they're also safe. So as you can see, there's a lot of misunderstanding sometimes that can happen because of lack of communication.
Well, if people have a few more minutes and you're okay to hang on for a minute,
Absolutely.
there's just a couple of other questions. I'll do the easy one first. I've asked Ed if he'd like to come on and ask his more complicated one directly. But Olive has asked if you could have data from space-based radar,
Mhm.
what kind of data do you think would add the most value? What kind of data would you prefer to have?
So this is a very interesting question. To be fair, I'm not an expert on that, so I don't want to reply. Let's say that I don't have my own opinion on that, but I can only refer what I've been told when it comes to people who are more expert. And for example, the discussions that we had also in these kind of workshops with the industry. So there are companies that are actually launching satellites to do space debris tracking from space. For sure, it's the more data we have, the better. So I would say that it's always useful. Even more so when it comes, for example, like one of the requirements actually that was not requirements, sorry, but enabling technologies or data sets that we could have. That was the result of these workshops, was to say that we need more accurate data, not just on the position and velocity of the objects, but also on the hard body radius, for example, on the altitude, etc. This is the kind of information that you can get, for example, more easily or with like a better accuracy from space. On the other hand, though, from what I understood up until now, the idea is that you would have to fuse this data with the data that is used on ground. You cannot just use space-based data for that. When it comes to radar specifically, I'm not an expert, so unfortunately, I cannot really, I don't have an opinion on that.
Okay, I'm going to give an attempt as I think Ed is still here. He's asked, given the altitude distribution of the debris and the constellations, to what extent does SGP4 XP meaningfully change the rate of generation of CDMs?
Ooh, okay. This is a question that I would have to turn towards my technical team, I think.
Absolutely fine. You've
And
put your
actually,
contact details,
if
so
I
Ed
can
can reach
find,
out.
yeah, exactly. If I have the contact details, I can actually reply to that in the next few days. But
No worries.
I don't want to say something I'm not sure about. So
And Martin, thanks. I know I
I will
appreciate
ask that to the technical team.
And Martin, you put your hand up and you took it back down.
Yeah, no, I was
I'll give
just
you the
not.
last word.
I will
No,
not forget, Martin. I will ask my technical team, and I'm sure that they know how to reply.
I love that one. I wasn't going to ask that one, but I mean, an interesting one to add to that technical one is: are we using more of the new specification of the ODM messaging system rather than good old TLE?
I'm
You know,
sure, yes.
even we've
So
moved on to OMM. At least it's only the beginning, I grant, but it's a start in the correct direction, I'm presuming. And it
yes,
does lead
definitely.
me to thinking about you say about shared data, and thank you, Roberto, for your answer earlier. Loved it. We can't get people to share data about trying to sustain spectrum.
Hmm.
Sharing data, you're right. We should all be doing that. I can't understand it. People just won't work together.
Yeah,
We shouldn't have separate agencies. These CDMs should be coming from one place. You don't have to answer anything. I think it's impossible. Um, I'm too old now and lost too much hair trying to get people to share things. Um, but it is the answer to the whole problem. If we had more data, like you said, I totally
yeah,
agree with you. We should share it, use it, and make a better job. But
Well, that's
definitely.
a very good trailer, Martin, for we will be having the Global Satellite Operators Association on a future GNOSIS Connect. They've offered to do one, and I know they're very interested in solving the problems of how operators can share data. And also just so that we don't end up eating up everybody's lunch period, I'm going to call a halt there, Gaia. Really appreciate you taking the time. Thank you very much. You've put your contact details up there, and I
Yes.
do see a number of people who have been here who might want to dig into more depth of technical detail about how you're approaching reducing those circles of uncertainty. So feel free to reach out directly to Guy. Our next Gnosis Connect is going to be with Connie Walker from NORLab. And that is scheduled on for 4 p.m., 1600, I should say, GMT on March 28th. So look out in your inboxes for that. And yeah, future webinars will include GOSA and others. So I look forward to seeing you at the next one. And thanks everybody for joining us today. Have a good rest of your morning, afternoon, or evening.
Thank you so much for the invite. Thank you. Bye,
Thank you,
everybody.
Gaia. Thank you, everyone. Thank
And
you,
please
Gaia.
send me the questions. I will reply in the next few days for sure. Bye bye.